Alright, materials and structures section for 2011. Again, I open the paper and I see the same sort of shape graph, and I feel comforted by that. But when we read the question, we find out this graph is actually slightly different. Engineers testing samples of different seal to determine the best type for construction of a bridge. The samples they are testing have a cross-sectional area of that and an initial length of 0.1 meters. Here's sample P, the force extension graph is shown. Now normally we're used to a stress-strain graph, and this is a force extension graph. So this is slightly different than what we're used to. And we take that into account. It certainly makes the most difference when we get on to question 4 and 5. But it shouldn't be too hard. Alright. It was different because we're used to stress-strain graphs for these sort of questions. In questions 1 to 4, the tension of 8.0 by 10 to the positive 3 is applied to the sample. Which gives the best? Following gives the stress. We know that stress equals force times area. It's the first thing I'll write down, and then I say, have I got enough information to solve that? Well, I've been given the tension force, and I know up here the area, so yes I do. So 8 by 10 to the 3 divided by my area of 2 by 10 to the minus 5. And when I calculate that, I get 4 by 10 to the 8. Which of the following gives the strain when the force is this? So again, I'll just write out my formula for strain. Change in length over initial length. And say, have I got enough information to solve for that? Well, what have I got up here? I've got the initial length, 0.1. Great. Divided by 0.1. Not point L. Change in length. I need that to work out the strain. But they've given me a force. How do I turn the force into the change in length? Well, I can use the graph. They've told me the force is 8 by 10 to the minus 3. They've said that at this point here. What is the extension? Extension means change in length. This means force. So at that point, 5 by 10 to the minus 4 is my change in length. And then I just calculate that, which is 5 by 10 to the minus 3. Alright, so I've copied and pasted the same picture for question 3 to 5, which gives the Young's modulus for the material P. So Young's modulus, I know, is either the gradient of the graph or it's stress over strain. And in this case, it's going to be easier to give me stress over strain. So I've already worked out the stress, which was from question 1. And this strain I worked out was from question 2. 4 by 10 to the 8 over is 5 by 10 to the minus 3. And when we calculate those, we get 8 by 10 to the 10. Which of the following gives the energy stored in the sample when a force of 8 by 10 to the 3 is acting on it? Okay, because this is where it gets different than what we've been doing in the past. For this is a note I want you to have on your cheat sheet. For a force distance graph, or force extension graph, same thing. Force, change in length. There's two things. One is the area under it. It equals the energy in joules. The second calculation is if you do the area under the graph and you divide it by the volume of the sample, then you get this unit energy, or energy per unit volume. That gives you the joules per meter cubed, which is back to front sort of thing of the stress strain graph. So have a note for this and have a similar note for stress strain graphs, so that if you get either of these graphs in the exam this year, you'll be able to tackle the area under the graphs, which are always the hardest ones in terms of these questions. Anyway, which gives the best energy in joules? It's given it away here, so we're doing this one here, which is just the area under the graph when a force of 8 by 10 to the 3 is acting on it. So here's this thing here. What's the area under the graph? Oh, awful. What's the area under the graph there? Well, it's a triangle, right? I don't know, my triangle is, oopsie, is a half base height. So that's what I'm going to be working out with. Half base height, which equals half times the base of my triangle is 5 by 10 to the minus 4 by, there's a 4, the height is 8 by 10 to the 3. 8 by 10 to the 3. And calculating those, you get 2. Easy. Alright, last one. Which is the measure of the toughness? Now, toughness is area under the graph or a stress strain graph to breaking. Look at the units here, joules per meter cubed. Because this is a force extension graph, we've got to do this one here. The area under the graph and then divide it by the volume, because we've got these units are the ones we've got, and it's a force extension graph. This is a force extension graph. So we've got to do area under the graph divided by the volume, and toughness is to breaking. So we're going to work out the area all the way to here, this whole area. What I'm going to do is I'm going to work it out, and you could count the squares in this one, but what I'm going to do for this one is I am going to do it as it's made up of a straight bit, a triangle, and it's made up of a flat bit, a rectangle. So my rectangle is about here. Let's do it in another colour. My rectangle's here. And my triangle is this bit here. And we'll do it down here. So we've got our triangle, and that is half base height, which is a half times the base of my triangle is about 7.5 from here to here by 10 to the minus 4. And the height of my triangle is 10 by 10 to the 3. Times those together, and I get about 3.75. My other section is this box here, which is the second part of it, and that's just base times height. So my base is this length here, and that goes from about 7.5 to about 17.5, so that's 10 by 10 to the minus 4. And my height is the same, 10 by 10 to the 3. So this bit here is equal to base times height, which is equal to 10 by 10 to the minus 4 by 10 by 10 to the minus 3. Let's just put those in brackets so you can see what I'm timesing together. It's the base times your height. When you times those together, you get 10. So the total area under the graph is 10 plus 3.75 equals 13.75. Now I've got to do, I've done this bit here, area under the graph, I've now got to divide it by the volume. So now my last section, 13.75 divided by the volume which is 13.75 divided by the volume of this is area times length. 2 by 10 to the minus 5 by 0.1. 2 by 10 to the minus 5 by 0.1. And those two, I'll do it in the brackets first, is 13.75 divided by 2 by 10 to the minus 6, which equals, my calculation gave me 6.9 by 10 to the 6. And the closest one we have is 6.6 by 10 to the 6. So there's my answer D. Alright, last question in the series. No. Engineers are testing another material Q. Here's the same force extension graph for P, and Q's been added to it. They decide not to use Q, they decide to use P, and why is that the case? Is it because P is stronger than Q? Well, no, because the strength is the stress till breaking or the force till breaking. So Q is stronger than P, so it's not the case. Is Q more brittle than P? Brittleness is the elastic region. So P's brittleness is this much. Q's brittleness is this much. Sorry, my mistake. Brittleness talks about if it has a smaller elastic region, it's more brittle. So here's the elastic region of P, here's the elastic region of Q. Q has a smaller elastic region, it's more brittle. So that is the correct answer. Let's just go through the rest. Compared with P, Q would stretch too much at a given load. Well, no, P would stretch a lot because it's got a, it's not as stiff and it's got a long elastic region. So that's not true either. And the Young's modulus for P is greater than Q. No, this is a steeper graph. Q's Young's modulus is greater than P. So the answer is B. But once again, the hardest ones in those ones were the question 4 and 5. Those are the ones you really need to practice. And to practice them with the stress strain graphs and with these force extension graphs. These area under the graphs ones are certainly quite difficult and quite time consuming. You saw from my calculations it actually took a while to get through them.